In the name of God, hello dear students. My name is Masoud. I'm a physics teacher. We are in Fairwell's website to explain physics curriculum, grade 12. So far we talked about some subjects in this grade 12, chapter 1. Right now I'm gonna explain new subject which is rigid rotating body. So what's the rigid rotating body? Let me explain. Let me read the definition for you, and after that I'll explain it for you. It says a solid body that preserves its shape. So it's rigid body should be a solid, yeah, should be a solid, and it should let's say preserve its shape. It should protect its shape. When every portion of it rotates with the same angular speed, with the same omega. Angular speed means omega, right? With the same omega and the same acceleration. Angular acceleration means same alpha, such as bicycle wheel. This one is bicycle wheel, and this one is merry-go-round, or we can say carousel. So what's the rigid rotating body? The first thing, the object should be, let's say, solid. This is the first one. So think about the solar system. Which part of solar system, let's say, is considered, for example, rigid rotating body? Let's say the objects that are in solid state, like especially terrestrial planet, right? Like earthy planets, like for example Mercury, like Earth, and like Mars. They are considered rigid rotating body. Plus what? Plus their moons. But Sun itself, Sun and all of the stars in general are not considered rigid rotating body because they are made of extremely hot gases. They are in, let's say, gaseous state. That's why they are not rigid rotating body, because you cannot apply these two conditions on the stars, right? Because center of the stars, right, rotate with a different omega and alpha than the atmosphere of the stars. That's why they are not considered rigid rotating body. And that's why the shape of the stars are, let's say, changes perpetually, right? The shape of the stars are changed perpetually, constantly, and you cannot say they are rigid rotating body. So a rigid rotating body, like what? Like the object that is solid, and every portion of the object should have the same alpha and omega. For example, think about this this bicycle tire. Whenever you choose a point on a rim of the tire, and you choose a point here at the center, or at the center of the, for example, wheel, or let's say in the middle of the radius, in each position, alpha and omega is the same. Alpha and omega is the same, except for the axis of rotation, right? So there's an exception here. There's an exception, except for the points that are located at the axis of rotation. So ignore this part right now. Ignore it. Just say, let's say, all of the portions of the object should have the same alpha and omega. In this situation, the object preserves its shape. And think about, for example, a merry-go-round or a carousel. This horse and the other horse, they are in different distances from the center of the merry-go-round, right? But they are moving. They are, let's say, circling with the same omega and alpha. That's why the object, the system, preserves its shape. Think about the situation. Maybe you say, teacher, what happens if one horse rotates with a different omega and alpha, let's say, compared to the other horses? In this situation, maybe this horse is thrown out from the from the, let's say, from the device. Maybe this part is separated from the device, and in this situation, the body cannot, let's say, preserve its shape. It cannot protect its rigidity. It loses its rigidity and it deforms, right, in this situation. And we have a lot of examples in your daily life. Think about a car, and the car, let's say, orbits or circles the square. Square, I mean a circular track. There's a car, for example. This car circles the square in the, for example, positive direction, counterclockwise. In this situation, all parts of the car should be, let's say, should be in the same alpha and omega, unless the object changes its shape, right? Let's say otherwise, the object changes its shape. For example, think about the door of the car, right? If the door of the car, let's say, has a different omega and alpha than the other parts of the car, than the body of the car, in this situation, the door of the car is opened, right? Maybe the door of the car is open, and actually in this situation, so maybe a dangerous situation is taking place. That's why for an object to be rigid, right, all portions of the object should have the same alpha and omega. These are conditions. Keep in mind that there are two conditions. What are these conditions? Same angular speed and same angular acceleration. Otherwise, the object changes its shape. So this is about the explanation of rigid rotating body. Right now, I'm gonna answer and discuss some questions with you. Question number 1. Use the figure of rigid rotating body. This is a figure of rigid rotating body to answer the question number 1 and 2. So this figure is dedicated for question number 1 and 2. Let me read the question for you. What would happen to the object, right? What would happen to this object if a point A, this point, right, had a greater angular speed than the point B? A greater angular speed. What happens if omega, mathematically, what happens if omega of A is greater than omega of B? Right? I told you. I'm sure you know the answer, but let's discuss it together. I didn't answer the multiple choices in order to go over the answer. Number 1, the object would rotate faster. Is it right? B, the object would rotate slower. Do you believe this? C, its shape would remain unchanged. Does it make sense to you actually? D, the shape of it would be changing. So this, let's say, option is true. That's why, let's say, this option is true for this question. Question number 2, which of the following is correct for 2 points A and B for a merry-go-round, right, rotating about a fixed axis? Which of the, let's say, and this question is dedicated for it refers to the what? The question refers to the figure. Which of the following is correct for 2 points A and B for a merry-go-round rotating about fixed axis? Let me let's say read them for you. A, omega of A is equal to omega of B. Is it true? Omega means angular speed. B, alpha of A is equal to alpha of B, means angular acceleration of A and B are equivalent. C, A and B, both conditions together. D, omega of A is greater than omega of B. I'm sure you know the answer, and I'm sure you choose the C. Number 3, for a rotating object, it's not actually about the figure. It's just in general. This question is about the objects in general. For a rotating object to maintain rigid, it has to do with the, let's say, figure, but let's say it's not, we are not focusing on the figure exactly. In general, for a rotating object to be rigid, every portion or point of the object must have the same one, must have the same linear speed. Did I explain? Did I tell you about the linear speed of the let's say points of a rotating object? I don't think so. B, angular speed. Angular speed omega. B, we read B. C, angular acceleration alpha. D, B plus C. So for an object to be rigid, omega and alpha should be the same. That's why B and C are correct options. Thank you guys for watching this video, and bye for now.